All right, we're back with more coding after quite a break. But let's jump right into it and let's continue the same series. This is called MIMO, right? So the same stuff we're used to. Let's keep working on the paper. Let's see, what do we have here? Yeah, this should be good to go. So let's remember where we picked off last time. I wonder if we had some diagrams from last time. Let's see, where did we leave off? Well, this is a nice overview. And I believe we did data generation for sure. We didn't do end-to-end system simulation, modern deep neural networks. What I wanted to do today, though, is to maybe also actually use the models in the paper, which are not that modern anymore, but we kind of want those in for exact reproducibility. And we got to fix some, oh yeah, we worked a lot on inverse problems last time, right? Let me see if we can find that here. Yeah, we talked about wireless channels too in some of the past episodes. We did chunking. Aha, it's gotta be here. Yeah, so there we go. So we implemented, implemented sampling. There we go. With this extra term here, with the consistency update. And I know we had some numerical issues that have to be fixed too. And I think that should keep us busy for a long time, actually. Okay. All right, so let's see what we have here now. I know I was on some sort of branch. Okay, so where did we leave off here? Let's see where the code is. Models. So we have a UNet, and I think I left a note. So we were seeing not a number. I remember now, right? That's because the inverse problem was degenerating during training. Where the inverse problem was solving. And I think I left a note for myself. One important thing is that we did not normalize the channel in the proper way. Where could it be? Actually, we didn't normalize the channels at all. Is there a fix me here? Yes, there is. There we go. So we get the pilot. So let's stop a bit here. Let's see. Okay. So why don't we do this? Why don't we practice how to, everything should still run here thanks to UV. Nothing changes. So we go UV run, MIMO train. Okay, good. Builds the package. And okay, so we have model formula and weights. Okay, it has a loss function. I think we're gonna sample at 500 steps or something, so we have to wait for training a bit, which is fine. I think we definitely didn't normalize the data, which is not good at all for diffusion models. And it's also, it doesn't reproduce the paper. So we're definitely gonna have to do that. Yeah, because the loss is too large from what I remember. And not only did we denormalize data, this matmul here, I know what the problem is, injects a lot of energy in the system. We'll see this right now. Because I leave in with pilots Yeah, so signal to noise ratio means that if this is my standard noise deviation, it would be nice if the signal power would be 1 and the signal to noise ratio would be 1 over the noise power, which is the squared standard noise deviation. But that's not the case here. The signal power is not 1 because it's proportional to the number to the system size, and we'll see that right now. I remember this. And not only that, the data on which I trained the model itself, which is a batch, for example, I believe this is not normalized. Okay, so it's kind of going down, but the learning is still stalling. Okay, it should, I hope it's, okay, sampling 500. Okay, so first it's sampling unconditionally, which should not... Okay, so this is another sign. If this one doesn't give us not a number, then the model itself is kind of stable, but then it's definitely the inverse problem part, or the conditional measurement that's not stable at all. Which is good, because we can fix that by normalizing the Y signal. Okay. There we go. Let's see what we have here. So, first and foremost, let me look at the batch shape. Okay, so we have a batch of data. And what is the mean? We want each entry to have, so the mean of the square, oops, of the absolute value of this across all axes. It's 1. And then just the mean, it should be 0, 0, right? 0, because it's an imaginary number, but it's approximately 0, 0. So the channels look kind of good, I think. But the problem is now, I know what the problem is. When we do this matmul, we inject a ton of energy. So the pilots also have a power of 1, exactly 1. In fact, each element is 1. But when I matrix multiply 2 vectors, so we can draw this a bit, okay? I know what's happening here. So let's fix the normalization for now. So I multiply 2 vectors, I take their inner product, and I get a single number, right? The problem is, if and let's say this has a size of what? Well, they need to have the same size actually, right? And what is, oh, the size is the inner dimension in my code, which is what? Val samples dot shape 64 and pilots dot shape. And 64 is exactly the number of transmitters, I think, which should be in data. Yeah, 16 receivers, 64 transmitters. Okay, so we can call this NT then. Now this is also going to be NT because it has to be like this for matrix vector for the inner product to work. So the problem is if the average power of this is roughly 1, and this is also roughly 1, and so on and so forth, then the average power of everything is roughly NT. Which is not good at all, because we would like the output to be normalized, to be invariant to the number of transmitters. Is this right? Signal to noise ratio. I think it's definitely one way to normalize the data, and I'm pretty sure this is how I did it. Wondering if it's right now. So we have so do I actually want this? So if I have a 1, roughly a 1 entry here, and when I multiply 2 Gaussians, so let's take a look at what the, so what is clean Y then? And how much power does it have in each element? Yeah, it has NT, exactly, right? So now I know how to fix this. If I multiply by 1 over numpy square root config data, or is it config? Or is it config data val dot dot what? Sample size minus 1, sample size 1. So if I do this again now, I fixed it. Yeah, so now the power is the signal to noise ratio. So the SNR is correct now because it's the received signal to noise ratio. Okay, so this is the definition of the SNR that we're going to use, and I think it's consistent. No, I'm sure it is. Yeah, it is consistent. So the SNR is the received power in each element divided by this noise standard deviation. Okay, so this should now clean up the gradients a lot. Okay, let's try again. Maybe this is enough. The thing is, I don't want to wait for everything. So how do we make this faster now? We gotta clean up the code again to focus on reproducibility more. Because I don't like some things already. So why don't we, yeah, we should finish this. But I really don't want to wait for that. So the sampling will make it every 50 steps, okay? And should we say sample unconditional, Boolean, false, sample conditional, Boolean, true, okay? So we want to skip the sample conditional. So we're just gonna do a trick here. So if config train.sample conditional else torch random like init. Well, actually, we can just pass init. Okay. No, sample unconditional. So that way we don't write an if, which makes the code look even uglier. We should set the model to train here and the model to eval here, also very important. Although I think inference mode does that. No, it's not. Never mind. And there we go. So recon samples. Oh, there's another mistake here. We can't sample from the model with the initial. We should also start from init, right? Yes. Complex to real init. Actually, this is wrong because we were starting from. We're starting right from the ground truth, which was messing. Ah, there's another mistake. Okay, good. So we actually need to start from random noise. Now there's another trickery here because wait, diffusion process needs to start the sampling from the first noise power. What is the first noise power? Because it's not 1, is it? Nope, it's noise levels of 0. There's a trickery here because it's also complex valued. So there's a lot of quirks here, right? Because we can't just sample from noise of power 1. It's actually noise level 0 times. Okay. Yeah, because the first step exactly happens at the first time step. We're gonna have to fix that time step too. A lot of quirks happening, which is good. Now there's another trickery here though, because this is a complex random valued, which has a power of 1 over square root of 2 times 1, or rather 1 over square root of 2. And once I go in with complex to real, and I sample from model, but the model is trained on what? Aha, so the noise standard deviation, wait, what is it added to? It is complex valued though. Okay, so this is good. So this is correct then. So this multiplies the noise in complex world. Okay. Should be a lot better now. Let's see. But my problem still stands that I can't train the model. The loss doesn't go down. Why? Why does the loss not go down? Let's see what's happening here. Line 129. Oh yeah, I need to return complex to real. Alright, because this passes through. Okay, again. Nah, still nan at step 100, still numerically degenerating a bit here. Okay, so I preserved unit energy. Let's see what's happening here. This is gonna be the hardest part for sure in the whole thing, because this scheme is probably very sensitive, which is kind of the whole point. What we're trying to reproduce, but that's good. It's clean Y. Noisy Y. Noisy Y looks in order, right? What is config data val dot measurement noise standard deviation 001. Random like. The model is not trained, but it doesn't matter. Why would it get stuck? So what is noise levels? Let's see. 0. It starts from 10. It goes all the way down to something very, very small. My beta is 1, right? Yeah. What's my alpha then? Or it's called step size, right? Alpha 0. Where is that? Maybe I should make this way smaller, like 10 to the minus 6. Let's try this. It's possible I'm way off with alpha 0. And I'm like exploding everything. 10 to the minus 3. Yeah, because it dictates. Yeah, it's the whole step size. Yeah, so. Yeah, this could be it. But I would like to train the model though. Do I really need a conditional model? So I can't fake the time step here. No more degeneracy. Oh, this is good. Oh, that was it. Okay, yeah. Well, a bunch of things we fixed. Oh, right. No more degeneracy. Okay. Oh, this is really good then. Alright, so we need to implement the grid search then. Because this is also the whole point of the paper, and part of reproducibility is how the heck we find these parameters, alpha, beta, because I did not put them in the paper, which is really bad, like very bad. They are in the original code, but not in the paper itself. So if somebody just reads the paper and wants to reproduce it, tough luck. So let's see, at least it's gonna save some plots, right? Yeah, I think. Oh, here we go. Conditional step 49. Yeah, it's these are estimated channels. They're crappy, but all right, I remember. So, okay, so we can make this plot nice too. Then, all right, let's clean up the plotting. Very good. Doing pretty good now. So, let's do it this way. We can delete these plots. Also, I saw a typo. Free Q. I don't even know if we have that. Free Q. Oh, I think we deleted that coding plot, which is fine. Okay. So why don't we do this? Why don't we make this plot nicer? So we can go back to 500 now, to plotting every 500 steps. We can also sample unconditional, sure. And so we put the model to train, very good, another important fix. Put the model to eval. So I'm gonna rename this branch, branch.m sampling fixes, okay? Then we're gonna do the NCSN part to actually reproduce the paper. And that should be it. Well, I still don't understand why the model doesn't train. How many noise levels do I have? 1000. And the max is 10. Nah, this should be fine enough though. Come on, really? Like I need I know in the paper I had 2311. Which is I know, and that value comes from the standard NCSN. Okay, before that, let me fix the plotting a bit. So what's happening here? I need a fixed size, right? It should be proportional, so we want 2 rows always. And we want this many number of samples. And the height of each. So I'm gonna have 2 times the number of receive antennas rows and 2 times, no, number of samples time, okay. So it should be something like 2 times. Actually, let me get these because this is so annoying me. Let me just unpack config data train. So it's 2 config data train, sample size, number of rows, and the other one is config train val batch size times config data train sample size 1. This is the size of the figure that's proportional, but the problem is this is gonna give me gigantic ugly figure, so we need something to proportionalize it. So let's do it this way. Plot ratio, we can just call this the int of this Well, we can do it this way actually. 1 divided by 0. So it's how many more columns I have in my plot than rows. So then the fig size should be, so these have to be in the inverse ratio. This is a 4, which is fine. So I can do this times a 4. And now my ratio is 4 divided plot ratio. So this is going to give me a plot, and this is 4. Plot ratio is also 4, so it'll give me a 2 times 16 plot, which sounds about right, right? Because I have 4 times more columns than rows in a single plot. Yeah, 216, the ratio is 8. Okay. Oh, okay, so I can just get that ratio actually, sorry. So it's 2, no, it's this. Okay, it's even easier then because it's this. Divided by 2 times this. Actually, I don't even need, I can just do division actually, right? And the fig size will be, I can just set the fig size in one place then, right? So it's a 1 to plot ratio now. But if I want more, then I can just say like 4 times plot ratio. Okay, so let's see, this should be clean up the plot a bit. I would really love this actually. I want all this stuff here. Okay. Oh, what's happening here? Oh, overwrite it. Okay. I messed up something here. Okay. 4, and this will be a 4. So 416. Yeah, 416 sounds like the right ratio for these types of plots. Again, here too. Okay. So fig size, and yes, we're gonna clean up this code, don't worry. We're cleaning it up, we're modularizing it. Now what I want to plot here is I actually want to do 2 plots in the validation because I need to also plot the, it's kind of the same story, right? So I need to plot the ground truth samples on top. Okay, so I have the validation samples on top, and at the bottom, where I just need this index, I now have the reconstructed samples instead of the synthetic samples. Okay, this should be a bit cleaner now. Don't understand why this... Let's not do this then. Let's try to plot even with NaN because I don't like how this, I don't like this logic here. Okay, so now if I run again, and let me plot after 100 steps. Okay, so there's some training. The problem is we still need to figure out why the heck the model's not training that well. The loss needs to go down. It needs to go down a lot. This is a pretty crappy model training. Okay, so now it's sampling the unconditional one. I really hope I got the plot right. Put the model in train. Now, there's two ways we can proceed from here. We can actually try to use the model, the neural network in the paper, which is probably the safer way, and I think I'm gonna do that. The other way is to try to fix this diffusion model we used, and I know what's happening here because we hard-coded the time step to 0. Oh, and we also have to fiddle with the noise levels, I guess. But this should be good though. The max noise level clearly overtakes the signal, right? Unless they want this like 40 or even higher. Also, this level is what? Am I squaring this or what's happening here? This is standard deviation. Okay, I got the figure exactly in reverse, which is not good. That's stupid of me. Maybe I'm confusing what this means then. Like fig size is in reverse then I think. So plot ratio, so the ratio is interesting. Maybe I don't need a tight layout. Well, this is easy to fix because we can do it this way. So here's what we'll do. Delete. And we'll put a false here. And we're just going to debug the plot. I should have done it from the start. And we can also give it 50 steps so it samples faster. And we can breakpoint here. And again. Okay, let's see how the picture looks. Okay, so it's not that interesting. So did I get the axis in reverse then? Am I really tripping or? Huh, interesting. I thought plots in matplotlib were height, width, fig size. Width, height. Oh my god. Okay, well, there we go. So the matplotlib is okay, this is the plot I wanted to make. Okay. What happens if I put a tight layout here? Do I get a bit more squeeze? Although it looks pretty good, to be honest. Okay, so I got the ratio in reverse. Pretty wild that matplotlib counts it width, height. So it breaks the PyTorch convention for a matrix. Number of rows, number of columns. I do get a bit more of a squeeze. Okay. This is fine. This is perfect. This is what I want. So I just want a tight plot. Clean plots for everything. And we can delete this. And now we can actually, let's see, what else do we do here? Oh, is there a breakpoint or what? Oh, no, there isn't. normalize data during it for inverse problems. But the real fix was that we changed the step size, and we're gonna have to set up a grid search. So now if I sample every 500 steps, this should be the final thing. Now, is it working? Not really. Because the model's not good enough. Is the loss going down? Kind of, but it's getting stalled. Actually, I should give it sample true true because I want to see both of them. So big noise error, so noisy data, pass-through model. This we can cut here, batch noise data, pass-through model, post-process output back to complex values. We can dump this comment here. Compute the loss function, update the model. Validate and sample from the model. So we can modularize this a bit, right? So sampling, what do we have here? Sample from model. So let's write some meta functions then. Define sample conditional that reuse this function. Unconditional, right? So it'll do the init by itself and it'll produce samples and it'll give it back to us real to complex. Okay, so we don't see anything from the outside. Okay, so what do we need for this then? We need all these 4 inputs. We don't need the conditional stuff. Not for this one. We also need the batch size because we need to tell it. We need to tell it. So this is config. Real to complex. We can drop this. Synthetic samples is sample from model. Real to complex. And noise levels are a list of float. Now, we don't need an init here. Okay. We just need the noise levels. Okay, so we do not need an init. That's good. But we do need a batch size though, unfortunately, and a sample size. And we can return the synthetic samples. Okay, so this will return a torch tensor. Okay, clearly this is not a good generative model, but something else I don't like is why do I have my data in quadrants like this? Is it some antenna spacing issue that I'm messing up the channel with? Obviously this is bad synthetic data, so the model has not learned too much. Yeah, and the estimation is not great either. No, yeah, nothing works here, or rather, the model is not trained enough yet, and the training loss is not going down fast, which is not good. Okay, so we'll finish modularizing this. Let me see, what else do we have here? Run to the terminal. Okay, we can actually work in a separate terminal while that thing is training. Yeah, training loss is not going down. So I need the sample sizes, right? So I need a batch size int for, well, no, and sample size, a tuple of ints. Okay, so then I can say batch size and star sample size. Okay, all right, so we'll finish this after a break. But yeah, the model's not training that well. We'll see how that's going after we come back. Just a quick break. All right, we're back. Let's see what's happening here. This model is still training, but the loss is not going down. Yeah, we gotta fix the loss. Before we fix the loss, let's go back to working on making this sampling a bit more modular. Okay, so we have the sample unconditional. Honestly, I should just eat this here, right? I don't actually need all this stuff. So why don't we do it this way? We actually don't need 3 functions. We can make this code even cleaner. We don't need the init at all. Okay, so that's gone. Instead, we can just request, hey, thanks for stopping by again. I remember you. Yeah, it's been a while. I wasn't able to stream the last weeks, but I'm back. We fixed the basic sampling degeneracy. It was just the step size, which I had to shrink it by like 1,000, but at least it's sampling now. But it's not a good model for sure. It's definitely not reconstructing or producing the realistic looking samples at all. But okay, so this is done training, but it was like a wasted run. We got, I guess I have to use the model I used in the paper, or the deep neural network I used in the paper, to make sure I can reproduce that one. So I did do a bit of prep there. We'll see how that's going. Okay, so let's see. So the sampling, we don't need the init. We can just start straight from here. Okay, and then we don't need this. So we don't need this. So I don't need anything actually. I can just use this sol function for everything. This allows me to absorb the init, because I don't really want to see this in my code. I don't really care. Okay. Okay, but now I need to pass what? Batch size equals config train dot val batch size, and sample size equals config data train dot sample size. Okay. If I want to sample unconditional, if I don't want to sample unconditional, what the heck do I do here? Because I lost the init, so I guess I'll just return a complex to real torch. I'll just return some fakes here, like a random, like val samples. And is the val data loader tied to the batch size? Yes, it is tied to batch size. Okay. Okay, so then I can also, I can cut the init from here. I need batch size, sample size here too. After noise levels. Let me just put these last. No, because they can't have defaults. Okay, I have to put this here too then. Config train.val. No, what is it? Batch size. Yeah, it is val batch size. And config data val dot sample size. And same thing, I have to pass a fake here. Okay, so I hide the sampling. Okay, then I also need a plot thing for sure. Let's see, so I need a plot. I guess I can take this whole thing. So we'll call it plot paired data or something. Can still live in sampling. So plot paired data. And it'll be like top row is a tensor. Bottom row is also a tensor. I think this is all I need to plot this. And let's see, so PLT. Okay, so now I got in first some sizes here because I'm not happy with this. Plot ratio, where did I get the plot? Oh, I see, yeah. So I need a plot ratio so the plot looks nice. Okay, and here's where it is. So let's see. So if top row input train data, it's complex valued 2D matrices, floating point. So this top row should be a 3D tensor. It's gonna have batch, height and width, but it's torch complex 128 or 64. So then first of all, I can't plot if I don't have the same number of samples. So that's a basic sanity check. So is not equal to bottom row. Shape 0. Raise. Value error. Cannot plot different top bottom row samples. Okay, so then I can take batch sizes top row dot shape 0. Actually, wait, they should all be the same, right? So the shape should be exactly the same. It's even easier. Cannot plot differently shaped. And I can just unpack this. So it's batch size. It's we can just call it HW. We can just call this BHW. Okay, so now the ratio is, because in the bottom row I have B times W divided by 2 times H. Okay, this looks a lot cleaner now, because I just want a figure size that looks proportional. And then for each B, okay, I have 2 times 2 rows and B columns. Okay, so 2 rows and B columns. And this one skips over a row of B's. And the top row is just top row. And the bottom row is just bottom row. Okay. And I also need a save directory, which is a path. And I guess I need a... Well, never mind. I can just take a save file then, which is a path. That's it. So now I just have to call this, which is a lot cleaner. So from also from sampling, plot paired data. So I can just do plot paired data. The top row is supposed to be the validation samples. The bottom row is synthetic, Okay, so true. And the save file should be this one. Config save train deer. Whoops. Okay, so this can all go away. And same for conditional. Which is actually, let's see what this comes out to. Run all. So the conditional also has a plot pair that's almost the same, except the bottom is the reconstructed samples. And this is called conditional. Oh, I don't have path there, sorry. So from pathlib, import capital path. Okay, this should fix it. Okay, this does fix it, yes. So we can try again. Now, what other stuff we can clean up from here? Yeah, we gotta get this, okay, all this pilot stuff has to go away. I guess it's fine for now, though. Okay, so this is pretty compact, but it, so the big one is for models. I have the unit 2D model, and when I pass a hard-coded time step in. This is the worst part. And can I remember what is the time step? Num train time steps. It's not even learned though. Oh, I messed something up here. Yeah. I'm passing sampling 51. I'm passing a complex somehow. What? Oh yeah, because I forgot to make this complex to real. Did I? Yes, I definitely did. And the convention is what? That it returns a... Okay, so then I'll do this then. I'll do real to complex also here. So then I don't need it on the outside. Yeah, I don't need to do it here. Okay. And I can also cut this. Okay, this simplifies a lot actually, yeah. I can do this. And I don't need this. For the NAND, it doesn't really matter. Okay, let's trigger this faster then. Yeah, okay, it's all good. Okay, so then I get back real, I'll get back complex values. So from the outside, I don't see anything here. The model times step 1. So I just sample and I plot. That's it. Sample plot. The only problem remains the conditional. It has a bunch of stuff here. Let's see. Can I fix this? Yeah, this should be clean too, right? Okay, so for sampling, we can also say define. Well, maybe this should live somewhere else actually. Should it live in data? Yeah, it should live in data for sure. Because this one gets the channels. Well, this one is create measurements. And I think all I need is the samples. Well, not really. Let's see. So I need to specify the downsampling factor of sorts. Okay, so this can just be samples, samples, samples. Undersampling. There we go. So I just need an undersampling, which is a float. Device. Damn it, I need a device too, because I'm tensor world. So I multiply samples with, oh yeah, and I need a noise power. Noise standard deviation, which is what, a float too. Okay, so this. I'm just gonna take this right shape here, shape -1. Undersampling is undersampling. So what do I do with the device then? Well, not much. I have to take it in, right? Maybe not actually. So what do I need here? I'm returning the noisy Y. Okay, actually I don't need, I'm gonna put the device on the outside then. Okay, so then I can just take create measurements. So from MIMO data, create measurements. Let's call it generate measurements. Okay, so then I can just directly get the noisy Y. Do I need a clean Y at all? Not really. Maybe for debugging. And the samples are the val samples. Undersampling is this factor. And what else do I need? What was the third thing? Oh yeah, the noise thing. Where do I have the noise power? Oh, it's right in this line. It's config data val measurement noise standard deviation. Okay. Measurement noise standard deviation. Okay, so then I can delete all this stuff. And no, I need the pilots too. Oh yeah, of course I need the pilots because I need that's how inverse problem work. I need to know the pilots too. And I'm just gonna give them two model device right here. Okay, this should be it now. Yes, I think so. Okay, this is as clean as it can get in the main loop then. So now it's just a matter of training a right model. Okay, so we cleaned the code up. We still have a lot of configs that have to be cleaned up. I feel like it's way too many config things in here. Should I give it more? Okay, let's see. Oh my god, I messed up the... Oh, because my samples are already on CUDA, right? Oh, then it's easier. Oh, I can get away even easier then. Hang on, because my samples are already there. So I can just say device equals samples.device. Okay, and I don't need actually, yeah, this is better because then I can cut this thing here. Okay, let me push this. So data. Modular, more modular code. So this looks way better now. Oh, actually we saved one line grand total, which is good. Okay, so we're pretty much done now. Now we can focus on training a model because we got sampling down to work. At least it doesn't degenerate anymore. The simplest, okay, so let me take a break. But I have one basic idea. Otherwise we'll probably end up doing the model from the paper. And that should be it. That should reproduce the paper for good. So I'll be right back after a quick break. Thanks for stopping by. Thanks for watching. All right, we're back. We're back, and we're back with more coding. We gotta fix the model training now because everything is pretty much done, right? So we have the yeah, we have clean code. We just gotta get the model training. Now, one thing I do here, I use this UNet 2D model from diffusers, which is fine, but let's actually take a look at the thing is, this is a score model. So let's see, Yang Song score matching, right? Generative modeling by estimating gradients of the data distribution. So this is what we want to do. Now, there are some computational tricks in this paper, which I think matter. Well, I have to reproduce because this is the paper I used in my paper. One of them, though, is very important. This is what we do too. The most important one is... Right, so we have the geometric noise sequence tool. We choose noise levels large enough to mitigate if it's small enough to minimize the effect. Okay, we kind of have this. So it's a unit. Okay. Instance. There's one trickery here. We have S. This inspires us to choose lambda. Okay. So the losses are weighted. This is very important, right? So the loss to get one unified objective. So the loss across a batch. Do I have this in my paper then? Oh yes, I do have it. Ah, I forgot then. Okay, very good. Did I forget to multiply with sigma on the outside? Then, in the code? Okay, that would explain a lot of things. Please say yes. Let's see. Loss. No, I didn't forget. No, I could not have forgotten this. Yeah, so it's square, square. Okay, so we did this trick. So square, square. Okay, what else do we have here? Okay, so he simplifies it here, blah, blah, blah. You can absorb this in, it's fine. Is this not the paper then? I guess it's not, it's the other one. It's called improved training, or what is it called? Improved training. Yeah, improved techniques for training score-based generative models. No. There's more tricks that we need to do. Okay, so this we have. Okay. Choosing noise scales. This we have, the smallest noise scale. Sigma 1, we don't care about this one. We can figure this out later. This is the trick. So we parameterize the score x divided by sigma, where Sx is unconditional. So today we use it as unconditional. Okay, sorry, let's see, I was here. So this is the trick. So parameterize the noise conditional score network by taking a neural network that doesn't depend on the noise and dividing it by the noise sigma. So we want this. This is what we're missing today, right? So for small noise, we want this to explode, or what's happening here? I guess. Okay, so then with this we can implement, because right now we put time step 1 here. So one thing I can do is I can let this go. I can let this be standard deviation index. This will make it actually conditional. Let's see how this behaves actually. This is already a way bigger change than it seems like. So git checkout -b NCSN. So if I just train with this, and you know what, I don't want to sample anymore, so I'll put my sampling to 100,000 steps, okay? And I just want to train to observe the dynamics. Last thing we need to fix. I'm trying to fix it with the unit. Of course, we can always bring the model in. So now I actually take it is a conditional model. Okay, the other way to do it is to actually follow the paper, which we have to do. We have to do anyways, because we want to reproduce it. So we get a model, which is a UNet 2D model. So why don't I do this? Why don't I just do a light wrapper then? A very light wrapper, like the lightest wrapper ever, right? So class UNet 2D model NCSN, okay? It inherits from a UNet 2D model, and we just need to override its forward method. Let's see, how does the forward method look? Because I want to divide by... So does it have a forward? Yes, it does have a forward. Self-sample time step, okay. There we go. So I need the signature. I need to import torch. And I need from, let's see, oops. From typing, import union, optional, okay? So now I need to rewrite this. So what I can do is, I can say output equals super dot forward with all the inputs, sample, time step, class labels, return dict, okay? And just apply NCSN v2 normalization trick. And I can do this. I can unpack output and apply, because right now today I unpack the output on the outside. I guess if I put return dict equals false, what happens? Maybe I should use return dict equals false actually. So sample time step class labels. Yeah, training is not going too well here. It's kind of going down, but maybe not as fast as I want it to. Maybe it is fine though. Nah, it's already oscillating. So how do we unpack the output? Oh, here we take the sample, which is pretty easy, right? So it's outputs. Okay. And I just need to do output equals output divided by noise levels time step. Now, Okay, this is all good, but I need self noise levels. So I need to also change the init method. So what do I need to do? Do I need to copy the init signature too? I guess I have to, right? Can I do the args trick? Quargs. I can, but the typing is gonna yell. Because then I can do super dot init with the same args and quargs. And then all I want to do is save the noise levels inside the model. Noise levels. And I guess I need this here because it's an extra. Okay. And that's it. So now I return output, which is a tensor, always. And there we go. So we modified the diffuser's unit to apply exactly the time step trick by dividing the output with sigma. Now, there is a trickery here because I think this needs... We gotta check the batch sizes. It's not gonna work if I try to divide. So let me try some shenanigans here. Import torch. So A equals torch random 4, 5, 6. B equals torch random 4. Can I do A divided by B? I cannot. So I need to give this, the only thing is this is a list and this is a tensor, so I just have to give this let me see what happens here. So now we're very close. Except the model now becomes what? It's not a Unit 2D model, it's a Unit 2D NCSN model, okay? And it also has noise levels, whoops. Equals noise. What do I have noise levels here? Well, I'm gonna need it for sure. And what is noise levels? Oh, here it is. I have a paradox here because the noise level go on the model device, but I don't have the model yet. So then I'll just go to CFG model.device, okay? And noise levels, and this is a torch tensor. Okay, interesting. So noise levels is a torch tensor. All right, so now I can, that's it. Let's see. Let us see. I do have a breakpoint, yes, I know. This should run now. Yep, okay. So we did the prediction. Okay, all is good then. So we have the prediction, which is a tensor. Okay, so this is the only trick. So output shape is this. Oh, I see it's also real valued. Ah, gotta be careful here. And time step is what? Yeah, there is a trickery here. Oh, actually, this is wrong. Oh, no, sorry, because it's noise levels of time step. Yeah, so these are the noise standard deviations, but these are complex powered. There's one more trickery here. I believe this should be divided by square root of 2. Because I actually have less noise in the real and imaginary part. That's trick number 1. Right? Is it? So let's see. So what do I measure? Noise levels. Add noise to data. Yeah, it is calm. Yep. Something sits wrong with me here. It's easier to think in reverse. It's easier to treat this as real and imaginary power noise separately. And then inside this function, just because this ran then eats a square root of 2. So multiply this with the square root of 2. So it's actually the standard deviation in the real and imaginary part. Okay, this is a bit sensitive here. I think I'm gonna do it this way then. So now on the outside, this is exactly what gets applied to the real and imaginary part. So the model can not do this because this works in real world. But something else depends on it too. The sampling does too. Here's the problem. This guy needs a boost now too. Because it's eating a square root of 2 again because, Unless, if I put a magic number 2 here, and I change this to a float 32, now it's good. Because the first noise level, and I don't need a complex to real anymore. Oh, it's thank God we modularized this because we would have to edit the code in like 3-5 places otherwise, right? So this paid off. So I think I'm gonna do it directly in real valued signals. I think I'm gonna do it this way, right? It is a bit abusing stuff here. Now everything is real world here. The conditional is fine. The conditional is a different story. Yeah, because you go to complex world with the current and you matrix supply, you do the thing. And this is fine. You want to get out in complex world. Okay, so I need a numpy here. We gotta be a bit careful. This is pretty sensitive. And that's it. No more square root tricks. Nothing. Again. Okay, so output.shape, yes. And the noise levels of the time step. Now these are directly, right? So self noise levels of 0, yeah, means on that, okay. Okay. I just can't do this division. That's the last thing I need to fix. Well, not really. Actually, I don't need to unpack the samples anymore. Sorry. So output. There we go. So we get the real. Okay, this simplifies my life actually a lot, because now when I get the output, I just get it. I don't need to unpack. Okay. Very close. So how the heck do I divide this? Now, is there a smart way to do this, or I can always do none, none, none? Is there a way to repeat the nuns? What? So what? Length, output, shape, minus length times step shape. Oh, sorry. So I know I need 3 nuns. How the heck do I get them there? So if A is a thing, which is 4. Oh, sorry, A is a special thing, I forgot. AX is a thing, that's 4. And extra dims is this. Can I do none times? No. Oh, I mean, I can do, sorry, comma. Wait, maybe it does work. It does not work. No. Star. Yes. Okay, this looks kind of horrible. Okay, fine. Extra dims. This is actually a nice trick overall because okay, so then I just have to do dot 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 star none. Okay, so I automatically put ones in the back. I think that's it. So now I should see the model train. Nothing too unexpected. Step 0. Okay, so no degeneration. Okay, it's going slower. So we didn't mess anything up. So the trick works in the sense that we didn't destroy anything. But does it really help convergence? Doesn't seem like it. Maybe we gotta be more patient. I don't know. Yeah, we need to train this for longer. Aha, the other thing is, I think my, let's put a 995 here. Because I'm pretty sure my smallest noise level is way too small, because it's like, yeah, it is, okay. So I know what's happening there. Let me see, where are the noise levels? Oh, they're right here, okay. Let me crunch this a bit here. So noise levels. So we start from 0 and we geometrically go down to -1, which when squared is, okay, now this one is too, maybe a 997. 7. I'd like to get to an SNR of 40, right? So how do I get to an SNR of 40? Well, the last one, so noise levels -1 squared. What did I do here? So noise levels 0. Why is it so compacted now? What the heck happened here? Am I dumb or it's the R? Oh no, sorry, I meant the 993 in the other direction. So I'm shrinking it even less now. All right, because I started from 099. Yeah. Okay. Okay, so we know that one is not good. So noise levels -1. This is the one. It's almost 10 to the -4. Okay, so then I just need to shrink it a bit less. So maybe a 3.5 here. I'll probably calculate this, but it's fine. Wow, this is so accurate, but I overshot it by, so maybe like a 3.3. There we go. Good. So we stop at minus. Okay, so we decrease a bit less aggressive. Batch size larger. Larger is always better, I guess. 128, 256. 128 should be the paper though. So let's see if this model works. If it doesn't work, we have to switch the model. We should switch the model anyways, but oh, I didn't mean to put the breakpoint here. So I compacted the noise range a bit. Not bad. So there is some more consistent learning. It's not jumping straight to a local minimum. Not bad at all. Come on. Did I get it? I may have gotten it. Come on. So it really is that sensitive. I think I got it. Basically, yeah, it was the division. So the division trick works. Come on. Yeah, it's going down pretty good. I remember this. I mean, this is how training. So it should cap out at like 20. There's another more complicated thing here. Maybe I'll do a separate stream, but the thing is, diffusion models can never have a zero loss. By definition, you don't want to see, well, they can't and you shouldn't want to see a zero loss, a zero training loss, I should say, in diffusion model training, but that's a discussion for another time. But this should go down nice though. Yeah, it's going down pretty nice now. So it was the division trick. So now I'm feeling even more confident. Let's actually use the NCSN. because it should be even, I would dare say, better. Come on, don't, yeah, it's not, don't cap out. As long as it doesn't cap out, we're good. Okay, so let's bring the other model in. So here's the trick. The trick is that I already prepared the repo because it uses, let's see, the other model uses this score as the PyTorch, but I already forked it myself. So what I'm gonna do is, let's add this with UV, okay? But after a quick break, we'll add this new repo. And that should be it, because this is exactly the model in the paper. And from an API point of view, from an interface point of view, it's very easy to integrate it, okay? So yeah, thanks for watching, thanks for sticking around, and we'll be back after a break. All right, we're back with more of the Disco Mimo content. Thanks for sticking around. Thanks for watching. And okay, so we kind of had a run last time. We had a training run, but wasn't really training to lower losses. So this time let's bring in the actual model from the paper, okay? and it's really easy because I kind of prepared ahead of time. So what we need to do is we just need to add the fork of my repo here and just import the model, and that's it. For that, I gotta check UV. So we just need to bring this fork in and boom, copy. So UV add git dependency. This is the only thing I don't remember how to do. Oh, here it is. So UV add at. Okay, so then we just do the package name is the thing is I packaged this. This may be a useful fork for other people, but I packaged this as a score SD PyTorch. So then UV will see it as a package. You can do UV add group torch score SD PyTorch. No, wait, what does it want? Quotes score SD PyTorch at. Is this what it wants? Yes. And then the address, which is git plus. Oh, I see. Wait, so what does it want? Git plus? Git plus this thing, right? Okay. Git plus this thing. Okay. Oh boy, I hope the dependencies are okay. It's looking good. All right. So it installed it. There we go. So now it's taken my fork and only added it to the torch group, and I can do whoops, sorry. I can do a UV sync. I guess I can do a UV sync. Group torch, okay. Just so we're sure we have everything, and then I can do a UV cache clean, and that's it. Oh boy, I had a lot of gigabytes here. That's good. And the log file. Okay, so then let's just add this. So git add UV log PyProject. Add score SD PyTorch dependency. But now this is a lot more reproducible, right? Because we have we pinned the repo down, everything is locked down. We did a bunch of changes last time, so are we still in the NCSN branch? Yes, we are. Good. So we fiddled with a bunch of stuff. Let's commit this too. And the last thing we need to do is just import the model and make it API compatible so that somebody can just switch between models. And that's it. Then we should use the NTSN model. Whoops. Git commit. Model changes. Okay, we need to push this up. I'll push it later. Okay, so then we go into models. And we say that from score SD PyTorch import. Why do I not see it here? Come on. Is it not seeing it in the environment? It must be, right? It must see it. Lib. Yeah, it's here. Score SD PyTorch dot models. I guess my VS Code is frozen or something. Well, let's try it this way then. Let's try in an environment. In a console, right? So I do UV run Python. Import score SD PyTorch. Okay, so it works. So from score SD PyTorch dot models, I need to remember where it is now. So where is this thing here? Score SD PyTorch models NCSN v2, the deepest one. Is there even a deepest? Oh, there is no. Is it NCSN PP? Did he change this or what's happening here? No, but I didn't change this since years ago. Oh, wait, this is score SDE. Okay. So this is a slightly different repo. I guess I'll have to use NCSN v2 64. I guess I'll use the 64 one, yeah. And what? It has the division trick, right? Yeah, there we go. It has the division trick. Okay, so it's from models.ncsnv2, import ncsnv2. Okay, so how would it look like? Let's see. Dot ncsn v2 import ncsn v2. Come on. It's triggering a torch. Yeah, okay, this is it. Okay. So I have this. I just have to learn how to initialize it then, because it's been a while. ncsn v2. Okay. Be nice if I can see the source code. Oh, I can. Okay, there we go. Perfect. So everything is all right in the world. Exit. Now, in order to initialize this, okay, so then I need a CFG model, which is a unet config. Let's see. Model. String. So if I say unet, it'll be a unet. If I say ncsn v2, it'll be ncsn v2. So then I go if config model arch, let's call it architecture, right? Architecture. If I say unet 2D diffusers, I want this one, which is still the wraparound, but it's fine. Else, if I say, actually, let's do a match. Okay, so we match this, and we do a case, because this looks cleaner, right? Yeah, and default. No, case default, what is it? Raise value error. Invalid model architecture. And then the case ncsn v2 pass. Is it really default? Python match case. Oh, it's underscore, obviously. Case everything else. Okay, so then I need a model, which is an ncsn v2. It needs its own config though. And the problem is that, well, yeah, the config is nested, right? So self-centered. Oh, yeah, we have to populate all this config. But it's still better than my paper, which hard codes all of it. So, yeah, we need normalization. Num classes. Yeah, so we have to track all these down. Model NF. Which I don't even remember what this is. Oh, this is the hidden dimension, right? Yeah. Number of features, yeah. Maybe it's not that complicated. Actually, it only has a pretty light config then, right? Activation. Okay, so it's not that bad of a config. Okay, so then we'll do it this way. Why don't we do it this way? Why don't we rename this unit config? Okay, and this will call model config. And now we can also make a NCSN v2 config, because we don't want to mix the fields in. And then we can say this is either a unit config or NCSN v2 config. I can't lazy annotate this, seriously. I need to move to PyTorch, whatever. And okay, so then we'll do post init then, right? If arch what do we call this? Unit 2D diffusers. Yeah, so I'm gonna take this meta config and I'll strip the config from it. Okay, I know what I'll do to make this clean, okay? So we say self config equals unit config. Else if, I can actually do the same match here. Self arch case, okay, case. NCSN v2 case raise value error invalid. Okay, now so once I have this, which is missing here, okay, then I can strip it from inside, but not here in the train. No, I'm not gonna say unit config, I'll just get model config, and CFG model will be I'll take it as a model config and I'll strip it from inside of itself, right? So where do I use CFG model? Yeah, but the typing will be bad here. So where do I use CFG model? Only here. It's not too bad. Model config. Problem is they all have different fields, so to get a clean cut solution there's no way, because this guy wants a stupid thing, this guy wants a nested thing. Yeah, NCSN v2 needs .data and .model in the config. That's it. This is the only place where it needs it. Image size. So I need a model and the data. Now, there's another, the cheap way is to just nest these in. Model. Fine, we'll do it this way. All right, we'll just create local classes that are not visible on the outside. And it'll be model is model and data is data. Because I need a dot map structure. I should really switch to Pydantic, but that's another story for another stream. Okay, so what config do we need here? There's an NF, which is number of features in model. Okay, so int. I guess we'll put the 32. We'll have to see how parameters explode. Data has a centered, which I assume is a Boolean, which may be true. What does it do with it? Self-centered? Does it do anything? So if it's not centered, it normalizes. No, so let's put this to true, because we want to do normalization ourselves, okay? What else do I need to use this model? Whoops, I closed it, sorry. Model NF, get normalization, model normalization. This one is big because in my paper I used, so this is a string instance norm. Okay. Anything else? NF, activation, model dot nonlinearity. Okay. String. What's the default one? Oh shit, I don't remember this one. Swish. Let's use swish. Okay, we are... get sigma's needs config too. There we go, sigma max, sigma min. It's what the heck does it want here? So it takes the log. Oh, this just gets it. He does the geometric progression by himself here. So I need three things then. I need model sigma min, sigma max, num scales. Yikes. I wonder if the problem is I have these already. So what am I supposed to do? I see, so he specifies it differently. Oh shit, this is gonna be a mess then if I have two ways to specify it. So if I put sigma max float, sigma min float. Okay, I'm gonna leave this as missing. And what was the other one called? Num scales. Int. What I want to do is nah, but there's no way to set these, right? Because this is gonna crash now. Yeah, this is really messed up actually, because we have two different styles of expressing sigma then. Okay, well, I'm forced to express it this way too then. Forget about it. Let's not even think, right? So we want this, and we're just gonna auto compute the R, which is actually a lot easier than it sounds. So now my noise levels, I'm just gonna use his formula then, because I kind of like it more anyways, right? So they're an exponential. Yeah, this is a geometric progression tool, right? Because it's like, so let's see. So it's gonna be torch exp. So it's the exponential of the torch lin space between the torch log. Well, let me just do numpy then. I don't have numpy here. So here's my problem now. I'm storing these in two places, so I can just magically say config max. Oh, sorry, max. And then config min, config model. And then the number of steps is config model dot, what is it called, num noise levels. Problem becomes, okay, so I have this, okay, and then I just tensorize these. Torch tensor, noise levels, device, config model dot device. We're done. Okay, so let me pre-commit this. Let's see what's happening here. Okay, I have this formula now, but I still store them in two places. This is really messed up. And actually, I don't know how to fix it. Wow, this is so messed up. I guess I can reinitialize it. Okay, I know what to do then. Okay, we'll leave these unset. I'm gonna do a trick here because I don't want to copy paste these both here and there. So I want to reuse the values in train, the config values here over here. To do that, I'll leave them uninitialized. But when I actually get the config, so, oh my god, it's even more complicated because this one gives me either this or that. So then I do this. If config model dot arch is NCSN v2, okay, populate sigma values, and I'll do it like this: config model dot config dot model is and now I have another problem because this class, well, this is insane. Like, I have another problem now because this class is private. Like, I don't have visibility. I really need to use Pydantic, holy shit, or Hydra or something. So I can't even reinitialize this, right? Okay, I'm just gonna write my own method then. Set sigmas. Okay, and it'll be self sigma max float sigma min float num scales int, and this reaches into self dot model dot sigma max equals sigma max, and so on and so forth. This is the only way to do it that's clean. Okay, so now I can, so now what I want to do on the outside is, what did I say? Config dot set sigmas with what? So I have to take the train ones. Config train dot finally max noise level, min noise level, num. Okay, so now I don't have to carry two sets of values around. So I just post set these. Okay, back to the thing now. What else do we need? Let's see, what do I have here? Okay, looks pretty good. Center true, these three guys were done. Okay, so done. What else do I need for NCSN v2? Config, 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 config. Channels. Channels is easy. What is it? It's data channels. It's 2. If I hard coded it there, I'm gonna hard code it here too. So int is 2 because we only work with 2D, or 2 channel data, not 2D. Sorry. And I think that's really it. Oh, image size. I guess the only place where this matters, there's a special rule if this is 28. I don't know what's happening here, to be honest. Like what, he puts so what do I need to do? Data image size? Oh shit. Oh, I'm just gonna put it -1 so it doesn't hit anything. Well, okay, fine. The right way to do it is I need to set this tool with exactly the same trick, okay? So then I do define set image size, self image size int self.data.image size is image size. And in order to avoid having double things, again, I have to set this. So where do I get the image size from? In config train? Nope, it's in config data. Data train. Same trick. If the model arch is NCSN v2, config model dot config dot set image size to, this is the data config sample size. I guess I'll pick the min of these. I don't even know why he wants that, but sure. Min of config data train dot sample size. Sure. Okay. So this should work now. So now we got an NCSN v2 model with NCSN v2 config. Boom. So all I have to do is control the arch here in model config, which is right here. So if I put here arch is, I can just change it here actually. Yeah. So arch is NCSN v2 there. So now I can change it straight in the main code. Let's try it. Let's see if this works. Breakpoint. So UV run group torch mymo.train. Oh, it's not mymo train. Oh, sorry, UV run -m mymo train because it's a module. Non-default. No way, I can't have non-defaults. Okay, just a tiny bump here. So my curiosity is what happens. Oh, is this not gonna work? Can I not have uninitialized stuff in data classes? Because that kind of defeats the whole purpose. I guess I have to guard these with none. Yeah, okay, so I can't have, okay. All right, so we're putting them back in the end. And I guess they all become none. And then the setter has to set them, yeah. I mean, the setter sets them. Oh shit, I have to use so mutable for few mods not I'll use default factory. What is that trick with default factory? I know what this is. It's omega conf. I can't just magically invoke a class. Yeah, so it's field, default factory, okay, like this. So from data class field, okay, gotcha. So from data classes, this is data class field, and he wants field. Default factory is, I guess, just the class, right? This is the only way to do nested configs. Let's see. This way works. Oh, it doesn't. Oh, again, I have a default thingy here. Where? What? Line 51? Oh, yeah, this config. Oh my god. I guess this is also none, right? Because post init. Yeah, this serves just as a meta router. I can clean this up, but I'll do it later. It's fine. Very close. 176. What? What did I do here? R? Oh, sorry. What is R? Oh, because I killed my sampling config. Yeah. Okay. Well, okay, we're very close, but the sampling config depends on the... I know what I did here. So... Unfortunately, the sampling config depends on the noise step decay rate, but I deprecated that one from the config. So then I have to recalculate it. What do I do with sampling config? Like, do I even do anything with the R? I do. I need, oh, okay, yeah, I definitely need the R in my algorithm. So what, how do I compute the powers now? So e to the log. Let me try this by hand. So I have, let's say, max. Max noise is 10. Min noise is 001. Num levels is 1000. And I say levels is exp of log, no, lin space between log max. Does lin space work in reverse? I hope it does. Okay. So levels. The first level is 10. The last level is 001, like I requested. And if I divide any two levels, I should get the progression, right? So for example, levels 0 divided... No, the other way around. Levels 1 divided by levels 0. And then if I do 2 divided by 1... No, 2 divided by 3 by 1. Yeah, it's the same. Oh, it's the same minus... Now the problem is... it's kind of the same. You would hope it's the same, but unfortunately it's not the same because of stupid floating point errors. Yeah, so in the last steps it actually gets I'm sorry, -1, -2 is the order, right? Last one divided by, yeah. So I'm curious about something actually. Here's a nice trickery because check this out. Does this matter? So let's start this way. So what if I decay my max? So I do 10 times this guy to the power of 999. Okay. But if I have a slight error, but at all steps, I guess you can argue this doesn't really matter, right? Yeah, so even if I get them all wrong, 999 times. So anyways, my point is that I don't have an R here, so I have to approximate it from Can I get the formula from R? I can, because it's max noise divided by min noise. It's to the power of 1 over num levels minus 1. The other way around. Min noise divided by max noise. No. What? So if I multiply the max 999 times with the ratio, I get the min. So the ratio is min divided by max. And I take square root of order num levels minus 1. Because it's a parenthesis, duh. Okay, there we go. This is the one I need. So then my R becomes CFG train dot max noise level, no, min noise level, divided by CFG train dot max noise level. Let me put it here. Everything to the power raised, or rather square root. Okay, 1 over train dot num noise levels minus 1. Now I'm starting to recognize this formula because I had it in my original code too. Okay, so now finally we can, so we restored sampling. Okay. Alpha is independent, this is good, outer steps, blah, blah, blah. This should work now. Again, let's try to train. And I was supposed to stop. Is it not CFG? What? Where do I take CFG? 53? What's happening here? Oh, I see. This is train. Sorry. CFG train. Max noise level, not model. Train, train, train. Okay, we're pretty much there. Okay, so what? I can't get the model get model. Models line 103. But is it not none? Or what's happening here? NCSN v2. Oh, I'm sorry. It's NCSN v2. Oh, I forgot to pass the config in. Duh. Okay, sorry. So it's CFG model dot. Wait. Oh, I see. CFG model is a model config now. Okay. And it's dot config. Okay, finally. So Right, because NCSMV2 wants the config, the inner one. Okay. Almost there. Aha, so I missed the config. Good, very good. What, is it NF? No. Inits conv.bias.data. Oh, so it's bias false. Is this a PyTorch 2.10 error? I think it is. I think this library has to be updated, but that's okay because I have control of the repo, so I can update it. That's why I forked it. What's going on here though? Yeah, this is obviously wrong. So somewhere he gets a layer with bias false. Okay. So set attribute set. Jesus Christ, this code is kind of bad. So he enters here with bias false. He should have done if bias here. I guess in older PyTorch, that bias was 0, but now they actually removed it or something. Well, let me try to fix locally. And if it does work, it's easy to fix it because it's my repo, so I can have control over it. Well, it's my fork, right? So this should be the fork. I mean, this should be the fix. Okay, that's it, we're done. We're past this. And what do you mean NCSMV2 has no attribute device? Is it not a PyTorch model? What's happening here? Oh, I see, but nobody placed it anywhere. Okay, so whoa, hang on. We have the model here, right? Yes. And we even have the parameters. Okay, so it's a... So what? PyTorch... Don't all the PyTorch modules have a device, or what's happening here? Did I not do 2? What is an NCSMV2 object though? So what if I do model.to CUDA? Okay, this is fine, but something fishy. This code is so bad. Like, why can't I? It's like, what the heck is this? This is not a regular PyTorch module, which has a device. Like, there's no self.device. So what? The UNet 2D model had it. Oh, come on. All PyTorch modules have device, right? This is so dumb. Well, I gotta look this up because this is so confusing. PyTorch module device attribute. Oh my god, it does not have. That means they implemented this. I'm so dumb. Okay. Well, okay, so we have to get the device, so we can't rely on... That's okay, we'll just use, let's see, where do we use it here? We'll just use CFG model.device. Yeah. Okay. It's not the end of the world. Here we go, also CFG model. Where else? 1, 2, 3, 4. Okay. Anything else? So we actually did get the model. The fix worked. Which I'll have to remember to fix in the repo. Okay, there's still a breakpoint because I want to see the data. Maybe I don't need that breakpoint though, actually. Where was it? Somewhere. Here. Okay. NCSMV2 forward. Aha, I have to unify the forward method too. Oh boy. Because this guy's forward takes as input X and Y. But then what is Y? It's the index of the sigmas. Okay, so this is easy to unify. There's another trickery here. Okay, sorry. The other trickery is that the interfaces of the way the models are called in Hugging Face versus this one are drastically different. So how do I call the Hugging Face? Oh shit, it has sample and time step. Actually, they're... Oh my god, I can do such a big trick here. I can just... These happen to be exactly the same, X and Y. With... Yes, I think they are. Yep, they are. Good. This is a nice trick because this works both for Hugging Face. It is a bit dangerous trick, but it's fine. We'll remember it. Model. And what else do I need? Sample from model. How do I call the model here? Interesting, I forgot this outer step in sampling. There we go. So current outer step. Okay, let's see. We're very close now. Where's the double? Where's the float? Seriously, I work with a double here? And why did the Hugging Face not complain? Because Hugging Face is more robust. It does numerical casting. So here's another interesting bug then, which we would not have caught. This is a double, right? Why is it a double? Batch noisy.d type. It is a double. Why? So what? The data is... Batch is a double too? No, it's not. It's complex 64, which should turn me into torch float 32. It's from the noise. No, it can't be. Is it the square root? Jesus Christ, if it's the square root of 2, I can't believe it. Is it? Is it NumPy that's dragging me up to double? So data, it's 64. Oh, please, no. Noise? It is. Wow. Or is it standard deviation? Oh, it is. It's standard deviation though. That's dragging me to float 64. It's not NumPy. So I do a full, yeah, okay. So this comes from what? From noise levels. Torch tensor, D-type, torch, float 32. This is dragging me to double, right? Yeah. So it's not really a new bug. I mean, it's not a bug. It's a we introduced it now with this new when we switched. Okay, that's good. There's some padding issues here. Almost. So where am I getting jammed here? 103. The third layer. So what, do I cut my sizes too deep or what's going on here? So let's see, output is my input size, right? Yeah, 32, 16, 64. Okay, so I jumped the channels up to 32. After the first layer, I have what shape? And after the second layer, I shrink down twice. And the next one breaks. So I enter with 832. Why can I not? What is self-res 3? Pad 1.1, dilate 2.2, kernel 3.3. Why? Why can I not? Res 3. So I go in with 2.2, resample down, act, dilation 2. Dilation 2, is it this one? It's gotta be the dilation. So I can't dilate something of size 8? Because my size is too small, or what's happening here? The shortcuts, the size returns shortcut plus output. So I gotta look inside the residual block, okay. Shortcut. Dilate, dilate. I gotta stop here, there's no other way. Shortcut. The thing is, this is the first block. Okay, so this is good. Okay. Next one. Good. This is the bad one. Okay. 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 Who ate 2 dimensions? Oh, yeah, what's happening here? So what is X? X was my input. And what is self output dim? Self input dim. Self resample. I gotta run through these one by one then. So output dot shape. It can't be this one. It cannot be this one. This conv eats 2 dimensions, or what's happening here? Yeah, it does eat. Okay, and I'm guessing this other one eats again. So it's a non-padded convolution. Well, it says padding 1. So conv 1. I don't think I can do the dilation here. My signal's too small. Yeah, okay. So no dilation then. Forget about it. I guess we'll try again. It's pretty bad though. Or is it? Oops. Okay, layer 3 dot shape. And layer 4 dot shape. Yeah, no dilation. Okay. Well, I kind of guessed this one, but good thing I remember some deep learning architecture stuff. Interesting. So we cannot dilate here. I'm gonna have to remember to push these fixes, but there we go, finally. Okay. Good. So loss is the same scale. Okay, perfect. So it's the same scale as the unit, and it's going down. So this is it then. We just have to train them out. It's going down better though. It's still diverging-ish. So now this should reproduce the paper. Why does it not converge? Maybe it's just a patience thing, right? Gotta be patient. Yeah, it's kind of going down. I needed to crunch. Come on. From what I remember, the loss used to be much better behaved though, like it would reach the tens. I can't even crack 400 now. What am I missing, I wonder? Maybe it is just a matter of being patient, to be honest. Like, let me try a wildly higher, larger learning rate. Nah, this one diverges. Oh my god, like it diverged back. Yeah, there's no chance with this one, right? Okay, so like this is super sensitive. Oh my god. Okay, well this is a disaster. So what, I should go like 0, 0, 1 even? Is it really that sensitive? No, this sounds too bad. 3 times 10 to the minus 4 is pretty good for Adam. Yeah, this is too slow now. Maybe not. Yeah, this is way too low learning rate now. So let me let the sampling go for a bit. Like, what if I sample after 1,000 steps? And I go back to 10 to the minus 3 to the minus 4. What am I missing? It's gotta be the data then. Data looks kind of sketch. These channels I got here. So oh damn it, so sampling. I can't use device here. I can't use device. Always forget I can't use device. Are the noise level on the device? They should be, right? Yeah, they are on the device. Okay. Again. What is it? What could it be? Is it the data really? Don't think so. I don't think so. More device? Wow. Okay, yeah, there is more device here, so let's see. Noise levels, device. Noise levels. Okay, this should be it. What could it be? If it is the data, how the heck do I fix it? Oh, it's the FFT shift. I know what's happening. Okay, so I know how to fix the data. Okay, hang on, I'm almost done here. Why? Oh, I see, because it wants a tensor here. There's another trickery here, because outer step can't be an integer. It's outer step times torch. Okay, because I need to broadcast this to everything. Man, I really need to. Okay, hang on. I'm gonna do this to like step 20 or something so I know we get past it. Long in byte bool. And what do I have here? What do you mean long in byte bool? So what am I passing? D type, torch, long. So it's not. Very close. Something is doubling me. Again, I have the double issue. Who is doubling? What is double? What? Is current Wait, how is this even? Oh, it's working because of because diffusers is smarter, it casts the data. So check this out, current is double again. No, it's not. Outer step. Noise? Noise. Wait, so my output comes out as 64? Is it because of the noise levels? I don't understand why. So why does NCSN v2 produce a 64 output then? Yeah, something, why? What? Because the used sigmas are 64, seriously? Damn, I gotta push these fixes. Okay, so we found some important fixes to a bunch of fixes to NCSN. Okay, there we go. It's sampling. And it's not well, we don't know if it's degenerating, but I guess it's not. Okay, so we can finally move back to every 1,000 steps. Not that this will do much. Let's see. And I guess in the meantime, I can prepare to... Let me go up. Let me clone this repo. I can actually patch it right now. Right. Yeah, this one is easy to patch. So which file did we change? Score SDE. SDE models NCSN v2, this one here. And what are the changes that we did? Do not dilate. And sigma's flow 32. I think that's it. So then I can do score SD PyTorch, get status, get add models NCSN, whoops, NCSN v2, okay. Git commit, fix for MIMO channels. Push straight to main, because yeah, I bypassed the rule because I'm the admin here. Okay. Oh, and that should be it. Now if I UV sync back. Oh, we got data. Let's see. Nah, this is not good, right? Yeah, this is not real data. Same issue as before. Let me sync again with the okay. While this is syncing, because now it should run out of the box because I patched that repo, so I can just upload everything. Ah, come on. Why not this one? Okay. So git commit. Oh, why is my computer so... Oh no. My visual code. Damn it, it's freezing. Add NCSN v2 model. We're pretty close, but it's gotta be some network thingy. Okay, so I can... I'm not gonna push it yet. Okay, so we installed this. So commit E47, which should be now. It is not, though. Oh shit, actually... There's a mistake here because I need the... I want the latest commit. So at... Let me copy the commit ID. I want this one. UV sync group torch. What? Oh, this is not how you copy this. So how does UV want to pin commit ID? Oh, I see, it's rev. Okay. So rev equals this. Rev equals this, right? Yes. Again. Why? Did I not like push what is this, 5747, right? Huh, interesting. Oh, is GitHub down again or something, or what's happening here? Because if I go to this address, I swear this works, right? Well, this is interesting. So what if I look at score SD PyTorch? Like I'm not... What? Does it not say 4 minutes ago, or what's happening here? I don't know what's happening here, but I do not know what's happening here. Should I clean the cache? Okay, well, this definitely works. Like, this is not a question of wild. I guess if I let it loose, it'll just pick the second to last one. Did I not copy the whole git commit ID, or I'm very confused? Yeah, like you would think this works. I guess it doesn't. So wait, can I use another commit ID? Like if I try this one? Yeah, it works. Okay, no, then this is a GitHub bug. Yeah, GitHub is down again. I think it's gotta be right. Is GitHub... Well, I don't know why. I don't understand why I can't see the commit ID though. Because this is a public repo. Okay, I'm gonna give up for now. But anyways, we're kind of on the right track. So we got the model. Thanks for sticking through this if you've been watching all along. But we got the model. We're kind of there, kind of not. We still need to fix this training. We'll figure it out. Yeah, thanks for sticking around. Thanks for watching. We'll see you next time. Hopefully, break won't be as long till next stream. All right, bye.